Have you ever really thought about how we shape the sounds we hear every day? You know, from the bass in your headphones to how clear a phone call is? Well, it all comes down to this amazing field called signal processing. And the best way to think about it is like being a sculptor, except instead of using stone or clay, your material is sound itself. So let's grab our virtual chisels and see what kind of sonic sculptures we can make.
All right, so here's our game plan. We're going to open up the sound sculpting toolbox. First, we'll look at the most essential tool of all, the filter. Then we'll figure out how to measure its power. You know, how sharp is our chisel? After that, we'll uncover this kind of weird, lasting echo that a filter can have, its ring. Then we'll get into the rules of the road, linear versus nonlinear systems. And finally, we'll see what happens when we throw those rules out the window to create totally new sounds through something called distortion.
Okay, first things first. Let's get to know the most important tool in our entire kit, the filter. This is our #1 way of carving away the parts of a sound we don't want and really zeroing in on the parts that we do.
So when we talk about all this stuff, what are we really doing? Well, it all falls under this big idea of signal processing. And honestly, it's pretty simple at its core. It just means using some kind of device, it could be a physical object, a computer program, whatever, to change a sound wave. That's it. It's the art and science of intentionally modifying sound.
And that brings us to the filter itself. So what is it? A filter is basically any device that changes the balance of frequencies in a sound. Think about it like this. A sound is made up of all these different ingredients, low notes, high notes, and everything in between. A filter acts like a strainer, letting some of those ingredients pass through while holding others back. So here they are, our 3 basic types of chisels. You've got your low-pass filter, which is great for carving away all the high, tinny stuff and just letting that deep, bassy sound come through. The high-pass filter does the exact opposite. It gets rid of all the low-end rumble and keeps the bright, crisp highs. And then you have the bandpass filter. That's our precision tool for when you want to isolate one very specific slice of the sound. All right, check this out. This is our raw block of marble. It's a complex sound before we've done anything to it. If you look at the graph on the right, you can see its spectrum is just packed with all these harmonic frequencies all across the board. It's a really rich, full sound just waiting for us to start sculpting.
And boom, here's our first cut. We just ran that sound through a bandpass filter. And look at the spectrum now. Almost all of those other frequencies are just gone. All we're left with is this little group of harmonics way down on the low end. We have totally changed the character of that original sound. Now, using that exact same starting sound, we can use a different bandpass filter, one that's set to a higher frequency, and look, we get a completely different result. This time, we've sculpted out a little island of higher-pitched harmonics. It just goes to show you the power of these tools. Same material, different chisel, completely different sculpt.
But you know, not all chisels are created equal, right? Some are really broad and some are super fine-tipped. So how do we talk about the precision of our filters? How do we actually measure the shape of the chisel we're using?
In a perfect world, a filter would just be a straight line down, an instant cutoff. But in reality, as you can see here, the effect kind of rolls off gradually. These sloped sides are called skirts, and the steepness of that slope tells you how aggressive your filter is. We measure it in decibels per octave, but all you really need to know is the bigger the number, the steeper the slope, and the more surgical your cut is.
Now, to get really technical, engineers use a few key terms to describe these filter shapes. You've got a couple of different bandwidth measurements, which basically tell you how wide the filter is. But honestly, the one that's most useful for us is the Q. Just think of Q as the sharpness of your chisel. A low Q is like a wide, gentle scoop. A high Q is like a razor-sharp point, letting you be incredibly precise. It's the number that really defines the shape of your tool.
Okay, this is where it starts to get a little weird and really cool. It turns out that our sculpting tools don't just affect which frequencies we hear, they also affect how that sound behaves over time. Every filter has its own kind of sonic fingerprint, a sort of echo that it leaves behind.
So to wrap our heads around this, let's just ask a simple question. What happens if you take the shortest possible sound you can imagine, like an instantaneous click, and you send it through one of our filters? What do you think comes out the other side?
So first, let's look at what we're putting in. That click is called an impulse, and in terms of time, on the left, it's just a single instantaneous spike. But in the frequency world, on the right, whoa! It's amazing. That one tiny click actually contains every single frequency, all at the same energy. It's like a burst of pure sonic potential. So we take that impulse, all those frequencies at once, and we shoot it through a broad, gentle filter. And what do we get? Well, as you can see in the waveform, we get this little burst of sound that wiggles for a moment and then dies out really fast. That is the filter's impulse response. It's literally the sound of the filter itself.
Now for the big reveal. We take that same impulse and send it through a very sharp, very narrowly tuned filter. And look at the difference. The output is this long, sustained ringing tone that just keeps going, long after that initial click is over. So here's the key takeaway. The sharper the filter is with frequencies, the longer it rings out over time. It's a fundamental trade-off.
And you know what this is just like in the real world? A wine glass. When you flick a wine glass, you're hitting it with an impulse. And that long, beautiful, pure tone you hear, that's its impulse response. The glass itself is acting like a super sharply tuned filter. If you put your hand on it to dampen it, you're making the filter broader, and that long ring just becomes a dull, short thud. All right, so we've gotten to know our main tools pretty well, but now we need to understand the fundamental rules that they play by. In the world of signal processing, pretty much everything falls into one of two camps. You have linear systems, which are totally predictable, and you have nonlinear systems, which can be wonderfully, creatively unpredictable. So here's the main difference, and it's a big one. In a linear system, what you get out is always perfectly proportional to what you put in. You make the input twice as loud, the output gets twice as loud. Simple. But most importantly, a linear system will never add any new frequencies that weren't already there. Nonlinear systems, they throw that rule right out the window. The output is not a simple multiple of the input, and here's the crazy part, they can create brand new frequencies out of thin air.
And this visual just makes it crystal clear. Just look at the shape of the lines. For a linear system, it is a perfectly straight, predictable line. That relationship between input and output never changes. But for a nonlinear system, the line is curved. That means the relationship changes depending on how loud the input is. And that curve, that's where all the magic and sometimes the chaos happens.
So what happens when we lean into that unpredictability? What happens when we use these nonlinear tools on purpose? Well, that's when we enter the world of distortion. And really, that's just a fancy way of saying we're going to break the rules to create some completely new sounds.
And this is the main idea right here. Anytime a system generates new frequencies that did not exist in the original sound, we call that distortion. Now, it's not always a bad thing. In fact, it's the secret ingredient behind some of the most iconic sounds in music.
Let's look at the first type. On the left, we start with a pure, simple tone. See how it's just one single spike on the graph? We send it through a nonlinear system and look at the output on the right. The original spike is there, but now the system has created a whole family of new spikes, new frequencies, at perfect multiples of the original one. That's harmonic distortion, and it's how we can take a simple sound and make it sound richer and more complex.
But it gets even crazier than that. What if we put two different tones into a nonlinear system at the same time? You can see them on the left. They don't just create their own nice, neat harmonics. No, they start interacting with each other, and the output on the right becomes this complex, dense jungle of new frequencies that are often totally musically unrelated to what you put in. That's called intermodulation distortion.
So where have you heard this messy, complex result a million times? The sound of a distorted electric guitar. If a guitarist plays a single note, you get some nice harmonic distortion. But when they play a full chord, multiple notes at once, you unleash a tidal wave of intermodulation distortion. That's what gives that overdriven guitar sound its thick, powerful, and kinda noisy character.
So, at the end of the day, these tools, these filters and nonlinear systems, they aren't just in some fancy recording studio. The very shape of the room you're in acts as a filter. The little amplifier in your smartphone creates distortion. Every single sound you hear all day long has been sculpted. So that leaves me with one final question for you. Now that you know the tools, how is your world being sonically sculpted in ways you never even noticed before?